Hello everyone. This is an overview session of the course, a brief, summary of the entire course, structure analysis by Professor Amit Shah. I am one of the course teaching assistants, Trisha Chakraborty. I am a PhD student at the Indian Institute of Science, Bangalore. We start why do we study structure analysis? The Basically, structure analysis is a process. It is performed before to the design stage. It provides the internal forces and stresses corresponding to the design loads, and it will typically account for the materials used, the applied loads, and the geometry of the structure or object. Basically, as civil engineer, one of our main tasks is to design buildings, bridges, design structures. So to design, what does designing mean? Designing means we have to decide the dimensions of, for example, in a building we need to decide the dimension of a beam, of a column. We need to decide what material to use, how much steel reinforcement to be given, and what is the criteria for that. That depends on how much load we expect the structure to withstand. So the structural analysis is the process where we are given a structure, we are given the boundary conditions and the loading, and the overall loading on the structure, and we find out the loads and displacements of each member of a structure, because then we are going to design each member at a member level. We cannot design a structure overall. So we will see what is the demand I'm expecting to come on a beam or on a pier or anything, and then we are going to determine the geometry and the material. So that is design, and the structure first structure analysis comes, then design comes. Now in structure analysis, around us we see a lot of three-dimensional bodies, a lot of complex structures. But for ease of analysis, they have the most common kinds of elements that we encountered has been classified, they have been simplified and idealized to some extent. And the kind of forces we encounter, boundary conditions, everything has certain idealization and to some simplifying assumptions to make our calculations easier and doable. So we start by looking at the okay. So this is the overview. Phase 1 is the analysis of determinate structures, and phase 2 is the analysis of indeterminate structures. So determinate and indeterminate are, the difference between the two is, uh, we will look at it later. The This is week 1. We are looking at and in week 1 we looked at types of internal forces, common classifications of elements and boundary conditions, structural indeterminacy, and bending moment and shear force diagram. So we start with internal forces induced in a structure. Basically, some external loading will be present in a structure. For example, when an earthquake comes, when a wind load comes, or when people are walking on a floor, or we have furniture, we have the building's self weight or the bridge's self weight. So these are the overall global forces coming on a structure. Now, what are the responses in the individual members? Like for example, in a beam or in a column, there is the most common, not the most common, but one of the most critical criteria for design is the bending moment. It is the moment that occurs when an external force is applied to the element, causing it to bend. Then the second one is shear force. Shear force is force that acts parallel to the cross section of a structural element when an external force is applied. So basically, if this is a beam, if this is a force, then it is called shear force. And torsional moment is a moment that is produced by twisting force. I mean, if we put the force like this, then the force is a shear force. The structure will bend like this. That is the bending moment. Now, if we provide a force like this, then we get a torsional moment, a twisting kind of thing. And axial force is force that acts along the direction of the body, axis of the body. So if we pull it, or if we push it along the axis of a beam, that is axial force. And this is how they look like. In tension or compression are the types of axial forces. This is shear. Here the cross section is like this, and the force is being applied perpendicular to it. In bending, this bending is the most easy to perceive. I mean, we see bending everywhere. And torsion is a twisting kind of moment. This is twisting about its own axis. Then the kind of elements we, as I said, that we encounter three-dimensional bodies. Obviously, everything we encounter is a lot more complicated and almost impossible to analyze if we do it exactly. So we idealize it, and a lot of structures we idealize in the 2D plane. For example, the one very common element is a truss element. It transfers only axial force, and the beam element transfers only shear force and bending moment, and the frame element is kind of a combination of the two, because they transfer axial force, shear force, and bending moment, all three of them. So now in the previous one we saw these are the four types of forces. Torsion is actually not that common and torsion is something that we would not try not to allow in a structure. So if torsion develops in a structural element, we generally try to increase the sectional area, or we increase the steel, so that the torsion doesn't come in the building at all. So the main kinds of forces we are concerned about are axial shear and bending, and this is how the elements are idealized based on what kind of force we will assume them to take. That that does not, of course, mean that, I mean, a structure won't know before that whether it is going to take axial force, shear force, or bending moment. It can be it can undergo any kind of loading, but in trust there is a certain kind of design that allows that may make sure that every element transfers only axial force, and for beam element as well. These are the kind of supports. Now obviously a structure is under some kind of loading, it also needs to have some support, otherwise it will be unstable, right? If this phone, I put a force on this, it will fall down. Till it has a support, it will not be stable, it will keep moving, and that is something we cannot allow. So we need to secure a structure with boundary conditions or supports. So this is there are the three main kinds of support. I mean, three idealizations. Again, these are the exact kind of supports are not available in the real world, but these are idealizations of certain kinds of support. So roller support, this looks like this. It is represented by these two rollers. It restricts displacement only in the direction perpendicular to it. So it will not allow the structure to move in this direction. It will give a force, a reaction force in this direction, but the structure can is free to move in this direction, and it is also free to rotate about the roller. Now the hinge support restricts displacement in both direction. It cannot move like this. The hinge for the, if there is a hinge, it cannot move in the upward direction. It cannot move in the sideways direction, but it can rotate. And the fixed support restricts displacement in both direction and out of plane moment. So it basically gives three reaction forces: a vertical force, a horizontal force, and the moment as well, because there can be no rotation as well. Now the phase one and phase two are basically broadly divided into analysis of determinate and indeterminate structure. That brings the question, what is structure indeterminacy? And this is what it is. Structures that cannot be analyzed using statics or equations of equilibrium only are called indeterminate structures. What does this mean? I'm discussing, they require other material properties to be solved, and the degree of indeterminacy is number of unknown reactions minus number of equations of equilibrium. Basically, if a structure has more number of unknown reactions, unknown is, I mean, again, a structure doesn't know what is unknown and what is not. When we try to solve it, we know these are the unknowns. But the thing is, a structure that has more number of reactions than the equations of equilibrium, it is an indeterminate structure. That means it is overly safe, basically. For example, this one, in this, in the 2D plane, there are, it is a 2D plane, so there are three equations of equilibrium: delta sigma fx equal to 0, sigma fy equal to 0, and sigma m equal to 0. And this is a cantilever support. This is a fixed support. So the fixed support also gives us three reactions. So it is like the degree of indeterminacy is 0. So this is a determinate structure, a stable structure. But the thing is, suppose one of these supports reaction fails. For example, suppose the horizon, this vertical thing fails in shear, then the structure will collapse. However, if you look at this is a cantilever beam with a roller support. So here, even if this support, this vertical reaction somehow fails, there is a backup to take that. I mean, there is a backup to take the vertical shear force. So the structure will not fail right away. So in the real world, we are always looking to making indeterminate structures to make them safe. Safety is our first concern in when we are designing buildings, because civil engineering in civil engineering, people's lives are associated with the safety of structures. So that is our obviously our foremost concern. So we will try to make a structure as safe as possible. So these degrees of indeterminacy are basically redundancies, that this, even if this support fails, there is someone else to take the force and the structure will not collapse. However, of course, we cannot make a structure infinitely indeterminate, because it will increase the cost. So civil engineering design is always a compromise between safety and economy. But safety is, according to me and according to all civil engineers, more important. But there is somewhere we have to draw the line. This is an indeterminate frame. This is another indeterminate frame, and let's look at this. External indeterminacy is total number of independent support reactions minus total number of available equations of static equilibrium. Now this total number of available equations of static equilibrium is a constant. In 2D plane it is 3, and in 3D plane it is 6. Why is it 6? because there is translation possible in three directions and there is rotation possible about three axes. So sigma fx equal to 0, sigma fy equal to 0, sigma fz equal to 0, and delta sigma mx equal to 0, sigma my equal to 0, and sigma mz equal to 0. Internal indeterminacy is total number of internal reactions minus available equations of equilibrium, and degree of total structural indeterminacy is the addition of these two. So there are certain formulas that we use to find external indeterminacy and the total degree of structural indeterminacy. And the internal one is a little more hard to perceive, so you can just find that out by subtracting the external indeterminacy from the total degree of indeterminacy. This is a determinant structure. This is the degree of indeterminacy from that formula is 3 minus 3 0. So this is a determinant structure. And now if the degree of indeterminacy is less than 0, for example, if there was only a hinge support here in this place, if there was only a hinge support, then the structure is not stable, because if you apply a load, it will rotate. It will rotate like this, and if there is any kind of movement, any kind of global movement, the structure is unstable. And unstable structures are not allowed. I mean, they're not allowed because we are designing a structure. We are determining how much force, what kind of movements we are going to allow in the structure, because that's what our job is as civil engineers. So unstable structures are obviously not allowed. We have to I mean, making a structure determinate is the bare minimum we can do. But in real life structures, we try to give some degrees of indeterminacy as well. For example, in this one, then in this one there are two fixed supports, so there are six reactions, 3 plus 3, and there are three equations, so this is 3 degree indeterminate. So suppose even if this entire fixed support fails, this fails, and moment fails, even if the fixed support, all three reactions of a fixed support fails, even then the structure will be stable. So there is a lot of redundancy in this structure, and this structure is of course much stable, more stable than this structure and this structure. And this is another frame with two hinge supports, so there are four reactions and three equations of equilibrium. So there will this is 1 degree indeterminate. So suppose one reaction of any of these hinges fail. For example, this somehow this the shear support fails and this becomes equivalent to a roller. Even then the structure will be determinate because there will still be three reactions. However, if one more support fails, then the structure will collapse. But that is what we want. We want a structure to fail in stages to give warnings. That is why indeterminacy is very important in a structure. And in phase one, we look at analysis of determinate structures, which is much easier to analyze. But in the real world, we mostly work with indeterminate structures. Now we look at the internal forces in beams. Before we talked about the four broad kinds of internal forces, but a beam element is one that only transfers shear force and bending moment. If it is in a condition to support, if it is under kind of loading where it will take axial force, then we will call it a frame element. It will not be a beam element anymore. So when we are studying beams in particular, then we are concerned only about these two types of forces. Shear force is this force that is transverse to the, this is the axis of the beam, and a shear force is the force that is transverse to the axis of the beam. So this is a shear force, and the kind of moment generated due to a shear force is a bending moment. So if we take the free body diagram of this part, we just take a random section AA and take a free body diagram, we see that this is the loading, then this is the shear force that is developed. I mean, to make ensure this part is in equilibrium, some kind of vertical direction force has to generate, that is the shear force, and some kind of moment also has to be generated, because if you take about this point, force is providing a moment, right? This p into this length, so an equivalent moment has to be generated to keep this in equilibrium. And since at this point A there can be no net, I mean, at this point also the force has to be balanced, force and moment. So on either side of the section, equal and opposite shear force and bending moment develop. And these are, I mean, this is how shear force and bending moment works. And the sign convention is another thing that is very important while working with bending moment and shear force, and especially for drawing the diagrams as well, which is one of the most important topics in this course. This is not the same as the kind of sign convention we have encountered in, for example, for while solving equilibrium, what do? We take that, suppose while solving while conserving force about in the x direction, we take that right forces directed towards the right is positive and the left is negative, or something like that. Or we take that anti-clockwise moment is positive, clockwise moment is negative. But that is not how we work here. Here it is like, if you are approaching a structure from the left side, if you are taking a section from the left side, then clockwise bending moment will be positive, and if you are coming from the right side, clockwise bending moment will be negative and anti-clockwise will be positive. And similarly for shear force, if you are approaching it from the left side, taking a section from the left side, upward shear force will be positive, but if you are coming from the right side, downward shear force will be positive. And shear force diagram and bending moment diagram are, as I said, one of the most important topics of the course. They are basically graphical representation of the shear force diagram and bending moment distribution along the length of a beam. This varies along the length of a beam. The shear force distribution and bending moment, there will be kind of a distribution that varies with this length of the beam. Like we take a section X, we take a general section X at some, I mean, A at some distance X from the support or from this side, whatever, that is up to us. And we will see that the shear force and bending moment can vary. For example, in this structure, if you consider the bending moment, if you if this suppose this length is X or Y something, then at this section the bending moment will be P into Y, because for equilibrium of this part, what do we see that about, if you take conserve moment about this point, P into Y, the moment will be P into Y. So basically the bending moment is Py at any section Y from the free end. So it will be a straight line that increases from 0 to PL, where L is the total length. So the bending moment varies. In this is a case where the shear force actually doesn't vary. You can see that any section you take, any section, random section you take, the shear force will always be V equal to P. So here the shear force diagram will be a uniform line and the bending moment diagram will be a straight line, increasing from the free end to the fixed end. For example, this is just a kind of complicated example that we take a, while drawing the BMD and SFD, we take the beam, we draw, we draw a straight line that represents the axis of the beam. And if this is a shear force, any place where there is a point load, there has to be a jump in the shear force diagram. So here there is a point load, there is a jump in the shear force diagram. This is basically a reaction. A reaction also acts like a shear force to the structure, because a structure cannot distinguish between a reaction and an applied shear force. To a structure, both are the same. Similarly, at a fixed support, a fixed support gives a moment restriction to the structure, right? So a structure will not distinguish between an applied moment and a reaction moment given by the cantilever end. And when there are distributed force, there tends to be linear lines of shear force diagram. We are not going into the details right now because this is just a general overview, but this is how they look like. And in bending moment diagram also, if there is a moment, applied moment, concentrated moment somewhere, there has to be a jump in the diagram, like this. And in bending moment, we see that when there is uniformly distributed load, the nature of the bending moment diagram is a parabola. It is proportional to x square. So we cannot exactly draw that like a linear. We can draw exactly, if we know 2 points of a straight line, we can exactly join it and find the shape. In parabola, we can only draw an representative shape, but that is fine. You are not expected to draw the exact shape so long as you know the basic nature of the diagram and the endpoint values. In any bending moment of shear force diagram, the endpoint values are see here the end values are written. So that is what is expected of you. Okay, then in week two, this was basically what we covered in week one. By BMD and SFD was a major topic. In week two, we focus only on trusses, which is one of the idealization. One ideal kind of structural element. And idealization of an idea and the way trusses are idealized, because real world trusses are mostly, first of all, 3D, but we analyze 2D trusses majorly because we can project it, we can extrapolate the response of a 2D truss into a 3D truss, which we are not looking at, but we are only looking at 2D trusses. And plus we take the truss elements as only straight lines, and we assume that they only transfer two forces, two kind of forces, tension and compression. That is because of the boundary conditions we impose between the members of a truss. And we look at stability of trusses. Stability has again to do with indeterminacy. An indeterminate structure is likely to be stable. An externally indeterminate structure is externally stable. Internally indeterminate structure is internally stable. But and some and then there is the class of just determinate structures where there is no redundancy, but if the number of reactions is less than the number of equations, then it will be an unstable structure. And there are two methods for solving member forces in a truss: the method of joints and method of sections. A truss is an assembly of two force members connected by nodes that creates a rigid structure. So this term two force member, what does it exactly mean? It means that there has to be pin So hinge support at both ends. There are a truss element and both ends there will be pin support. A pin support is something that transfers translational forces in both directions, in two perpendicular directions. So between two members of a truss, only a force in the x direction and a force in the y direction is transferred. There is no moment that is transferred basically. So that is why a truss, every member of a truss individually behaves like a member that can only take axial force. It can carry no load in between. Loading in a truss can only be at the nodes or at the joints, and it can only have two forces acting upon them at the hinges. Each hinge transfers only two forces, and the member is only under axial loading, no shear bending or torsion. I mean, in a truss, overall there can be any kind of loading, but we, but the members, the way the force is transferred between member to the support finally, that the mode of transfer is only axial loading, and this is how this is the pin support. Suppose this is a member of a truss, this is a pin support, this is a pin support, and there are there are two forces in perpendicular directions. I mean, we can split that. That is up to us. We can split a for in any kind of force in any direction. We can split it into mutually perpendicular directions. But the resultant here in a truss always has to be along the member length. Types of axial loading are tension and compression. Tension attempts to elongate the member. Tension acts like this. In a member, tension acts away from the member in both direction, and compression works towards the member in both directions. So compression attempts to shorten the member, tension attempts to elongate the member, and these are the two types of axial loading that we will encounter in trusses. And this is, for example, an idealization of a truss. This is a 3D 3 dimensional body. There are basically two trusses in this plane and in the plane behind it. We idealize it like we take these members, we represent each of these members as a straight line, and these joint points as the joints as our pin supports. And stability of trusses, there are two kinds of stability: external that we are concerned about, external and internal. External support, in external we there must be set, the criteria is that the three equations of equilibrium must be satisfied, all support reactions must not be parallel, and all support reaction must not be concurrent. For example, in this, all support reactions, there are three roller support, so they all give force in the vertical direction. But what if I apply a horizontal load? The truss will simply move because there is no one to stop the, I mean, there is no one to provide a horizontal reaction force and stop the horizontal translation. So this is a linearly unstable truss, and this is a rotationally unstable truss because every support reaction passes through this one point C. So if a moment is applied about C, the truss will rotate like this globally. And internal indeterminacy is internal stability is no part of a truss can move rigidly relative to another part. Where now this is a formula. Number of members required for geometric stability is 2j minus 3, where j is the number of joints, and the members must be arranged such that the truss can be divided into triangular blocks. This structure is, I mean, this is externally stable because there are two at the hinge there are two support reactions. At the roller there is one support reaction. So externally it is stable, but internally this part can collapse upon itself. In a truss, you have to join. I mean, there has to be one minimum member here. And the interesting thing about this truss is, if you do this 2j minus 3 formula, there are six joints: one, two, three, four, five, six. This is not a joint unless there is a point drawn here. This will not be a joint. The number of members required we see is 9, and there are nine members here, but there is a presence of a rectangular block. So this means that this part is overly stable and this part is unstable. So you can take one member from here and join it here, then it will be a stable structure. The method of joints is, it is suitable when forces of all members are to be calculated. It is a little elaborate process. At each joint, there are two equations of equilibrium. Like I said, a hinge support transfers two forces, so that is, and the method of joints cannot be applied if the number of unknown forces at a particular joint is more than two, of course, because we have two equations of equilibrium. We can only solve two forces at a joint, and this is the sign convention. Like I said, for tension, arrows point away from the member, and for compression, the arrows point towards the member. This is the sign convention we use. Tensile is positive and compression is negative. Sometimes it's taken like that. And the method of sections, it is suitable when forces are required in only few members. So it is kind of a shortcut, or if you need, if in MCQ questions you are asked about only to find what is the member force in this member, a member from the middle of the truss, then if you use a method of joints, you have to start from the reaction points. You have to go up for every joint, solving the member every member along the way. But here you can simply, you can cut the whole truss into portions via sections, and the equilibrium of each portion is considered globally. It is not a joint wise anymore, and three equations of equilibrium must be satisfied in each portion. This is how you can just cut a section, and about this section, this part has to be in equilibrium and this part has to be in equilibrium, and these are the three criteria. Then in week 3, we looked at the other. There is another kind of response that a structure shows apart from the force response. So far, what we have done in beams or in trusses, we have been concerned about the axial force generating in the truss, or the bending moment and shear force generating in the beam. These are the force or the stress kind of response, and the other kind of response is the strain or displacement kind of response, and that is also important because while we are designing a structure, there are two kinds of criteria which have to keep in mind. One is the collapse limit state, that is, the structure must not collapse, it must not be overloaded. That means that it cannot be loaded beyond its capacity, the beyond the force it can take or the stress it can withstand. There is another kind of limit state that is called the limit state of compatibility. That means that a structure cannot, there also has to be some kind of deflection limit in structural elements. You cannot let a structure deflect beyond control even if it does not collapse. Even if, suppose in a factory there is a beam, the beam is deflecting, the beam is bending, it is not failing, it the force generated on it is not more than the stress or force it can withstand, but it is bending, so it can hamper some. For example, a machinery, in the machinery needs to be taken, it needs a certain amount of clearance. The beam can, if the beam is deflecting too much, it can hamper all that. So there are deflection or displacement criteria on structural elements as well. So we also need to look at the deflection, how to find out, given the loading on a truss or a beam or a frame, we need to find out how to find the displacements. So there's a principle of virtual work, which is a very very basic principle, and it has very wide applications all over this field of structural analysis. Unit load method to determine displacement in trusses at the nodes. This is the principle of virtual work. Basically, this the work done by a force can be conservative or non-conservative, as we have studied in our plus 2. The work, when the work done is path independent, like gravity, whatever path you bring it from one point to another, only thing that matters is the distance with the height difference between the two. It doesn't matter if you bring it like this or just straight down, the work done will be equal. And non-conservative force, for example, friction, we know that it is dependent on the path. So if you take a body along a zigzagging path, if it covers a greater amount of length, then more work will be done by the force. This At equilibrium, a structure, this is the principle of virtual work. Basically, at equilibrium, a structure deforms such that its potential energy is minimized. So external loads must be equal to internal forces, and external work must be equal to internal work. This work done by a real force, this is the phrasing is a little different, but so by now you should be used to it, because we have used the principle of virtual work in several weeks. I mean, mostly to find deflections of all kinds of structures. Work done by a real force acting through a virtual displacement, or a virtual force acting through a real displacement. And the principle of virtual work says that in equilibrium, the virtual work of the forces applied to a system is zero. The net virtual work carried on by all forces should be zero. The unit load method to find deflection of trusses. The response of a structure, as I said, that force and stress displacement, the force and stress response, the collapse limit state, and displacement of strain, the serviceability limit state. And in a truss, member forces and nodal displacement are what we are basically concerned about. So in week 2 we looked at member forces, and in week 3 we looked at the nodal displacements. And the nodal displacement we use for solving the unit load method, which is based on the principle of virtual work. The technique to quantify displacements and rotations of equilibrium configuration of a structure, that is the shape of a structure after it has managed to equilibrate the applied forces. And virtual unit force is applied at the node where we want to calculate displacement. Analogically, virtual unit moment is applied to the node where we want to calculate slope. Slope, basically we say displacement or deflection, but we basically mean translational displacement as well as rotational moment, slope. For unit force, external virtual work is 1 into delta. So since external virtual work equal to internal virtual work, delta equal to the internal virtual work, and delta is what we want to find out. These are the steps, I mean, we use to calculate the displacement of any one joint, like delta c of the truss. These are okay. I mean, we won't go into the details because have been a lot of problems solved on these. These are the basic steps. Then the way we looked at deflection of beams, we also have to look at deflections. We looked at deflection of trusses. The same way we have to look at deflection of beams as well. And there are three methods mainly: elastic curve equation method, moment area method, and conjugate beam method. These are the term. Okay, so the terminologies in beam theory, we need that some basics and some assumptions that we use. So neutral surface, a beam is formed of many fibers aligned longitudinally. For longitudinally means along the axis. So there are a lot of fibers like this under the action of a transverse load. In a beam we expect it to be under transverse load. We do not expect it to undergo axial load. So when it's under transverse load, the fibers near the top of the beam contract. For example, if you see if it is bending like this, if it bends like this, the fibers near the top will shorten. It is under compression, and the fibers near the bottom are under tension. So there is a plane in between where the fibers of the beam do not change their length. That is the neutral surface. And why is it a neutral surface? Because the beam is a three-dimensional body. This is a line. This is basically the neutral axis, and the surface is the surface along the neutral axis that goes into the plane of the structure. And this is the neutral axis. The axis of the beam is the interaction of the neutral surface and the longitudinal symmetry. And deflection curve, when a beam is loaded, the neutral axis or surface deforms into a curve, which is called the deflection curve or elastic curve. It is basically it is basically a variation of y with respect to x, or w. Sometimes we say that w or y is the vertical displacement, and it varies with x as x goes from this point to this point. So at every x there will be a certain amount of vertical deflection. That is what we call what I mean, that y of x equation or the w of x equation is basically the elastic curve. These are the Euler-Bernoulli beam assumptions. The kind of, I mean, assumptions are simplifying. Simplifying assumptions are what we assume to make our calculations direct, straightforward. But the assumptions are also a limitation of a theory, because they assume something, and if that is not followed, the theory is not applicable. So these are the beam common Euler-Bernoulli beam assumption is one of the simplest beam theory assumptions. So there are three main clauses. The beam is infinitely rigid in its own plane. According to this assumption, there is no deformation in the plane of the cross section. Then the cross section of a beam remains plane to the deformed axis of the beam, like this. When it is bending, this section becomes like this, a straight line. It is a straight line, and into the plane it is just a plane surface. It is not a warped surface. Like it is not becoming a curved line. It is still staying a straight line, and moreover, the cross section of a beam remains normal to the deformed axis of the beam. Like initially, when the beam was undeformed, the neutral axis is oriented around x, and every section is oriented along y direction. So that is at 90 degrees. But if it bends, then even then we will assume that this angle remains 90 degrees. These are the governing differential equation for beam that you have to remember. That is the part of the Euler-Bernoulli beam theory. Moment, and Q is shear force and M is moment. So W is transverse or vertical deflection. X is distance along the beam, and E is Young's modulus. I is the second moment of area. It is moment. The I is the moment of area, or the moment of inertia of uh, the cross section of a beam. And M, Q, and W vary along the axis of the beam, functions of X. And we know M and Q from, remember, the bending moment and shear force diagrams are basically M of X or Q of X, the variation of bending moment or shear force along the axis of the beam. From that, using this equation, we can differentiate it twice basically. You can see that if you integrate this equation twice, you can find W as a function of X. There will be certain constants of integration. That is where we apply the boundary conditions. Because suppose it's a cantilever beam, and we are going from the fixed end to the free end. X varies from 0 to L. Then we know that at x equal to 0, there is no deflection because it is a cantilever beam. So we know that at x equal to 0, W equal to 0. Then we also know that there can be no slope at the fixed end. So at x equal to 0, W dash is 0. The slope here is dW dx. So these are the two, basically when you are When you're solving a two second order differential equation, you need two boundary conditions, and that we always get the two boundary conditions from the beam if you study the beam equation itself, the beam configuration. Then there is a kind of compatibility or continuity conditions. They are essential for solving indeterminate structures considering the displacement equilibrium of the structure, and they need to be satisfied for determinate structures as well. The concept is at a single point in a structure, there cannot be more than one displacement. There is horizontal, vertical, or rotational. At any one point, like if you come from this side, if you come from this side, for example, this is a roller support. Whether you see from this side or this side, the net deflection, the net slope at this point has to be the same on its immediate right and immediate left. Because if the slope are different, that means there is a discontinuity in the structure. That means that is an incompatible deflection pattern that we cannot accept, and otherwise there will be discontinuity that is not allowed. Displacement and at any point on the beam must be the same for all time, and there can be no sudden changes in the displacement at a point. There can be no jump. Like for example, in a shear force or bending moment diagram, there are jumps. Like when there is a concentrated force, the shear force diagram will show a jump, but for displacement or rotation, that is not allowed. Then uh, this was the elastic curve method basically by twice differentiating this governing equation. This is the most basic one. This is, I mean, based on this we using some simplifying, not simplifying, that we put it in a framework, put the solving of these equations in a framework, and we end up with two methods: moment area method and the conjugate beam method. They give the exactly same results, and they just have a kind of different kind of phrasing that they can be solved more easily. So the change in slope between any two points on the elastic curve equals the area of the m by ei diagram between these two points. So we know we can draw the bending moment. This m is basically the bending moment. So we can draw the bending moment diagram, and we take, if we are concerned about 2 points A and B, we will take the moment diagram between A and B, and by EIC, Young's modulus and moment of inertia are generally constant, so we can just divide the values by EI, and the area of that is basically in the 2D plane. The way we draw it will be a trapezium or a triangle or a parabola, something like that, and the change in slope, the difference is theta A minus theta B, will be the area enclosed within the m by ei diagram. And the theorem 2 says that the vertical deviation of a point B on the elastic curve, this is the elastic curve, the deform shape, with respect to the tangent which is extended from another point C, equals the moment of the area under the M by EI diagram between those 2 points B and C. This moment is computed about point B where the deviation from B to C is to be measured. Basically, from C we draw a tangent, and this is the quantity that we are finding out, the different distance between the reflected point B and and this projection of the tangent. So here we take the M by E diagram between B and C, and we take its moment about this point B to find this. And this is the conjugate beam method, a structure analysis technique used to analyze beams and frames by transforming real beams into imaginary or conjugate beams. We apply principles of virtual work and static equilibrium on conjugate beams to solve for unknowns and understand the behavior of the real beam under various loading conditions. This is basically the principle of duality between real beams and imaginary beams. That means a real beam is subjected to loads and support conditions. That is, we want to solve. We want to solve the deflection of a real beam. It is transformed into an equivalent imaginary beam. That is also a beam that we call the conjugate beam, that has the same length as a real beam, and it is subjected to loads equivalent to the bending moments along the length of the real beam. Basically, we suppose we have a beam, we have some kind of loading pattern, so we can find out the bending moment diagram. Suppose it is a triangle. Suppose in a cantilever beam, the bending moment diagram is a triangle that is 0 at the free end and PL at the fixed end. So that triangle is equal to the loading in my conjugate beam. That it will have a triangular kind of loading, and the transformation simplifies the analysis process in this manner. Firstly, we see how the rules for loading in conjugate beam. The M by E diagram of a real beam is load on conjugate beam. Sign convention is the same as that of bending moment. You just draw the bending moment diagram with sign, and you put the same that load. When is the bending moment diagram there is positive, you put positive upward loading, and if the bending moment diagram is negative, put downward loading. Positive or sagging moment beam is upward load, negative or hogging beam is downwards loads, and this is out. This is the bending moment diagram. Then this is the loading on the conjugate beam. This triangle kind of thing. And the rules of boundary conditions in the conjugate beam is, suppose in a real beam you have a fixed support, in the conjugate beam it will become a free support. If if in the real beam you have a free end, in the conjugate beam it becomes a fixed end. This is the principle of duality basically. I mean, whatever there is, the conjugate beam of a real beam is the, I mean, suppose from a real beam you get a conjugate beam, and from the conjugate beam you get a real beam. The boundary conditions will be the same. I mean, the boundary conditions will be dual. They will be in pairs. So a hinge support remains a hinge support. A middle support, like this is also called a knife edge. Like a hinge support is at the corner, and if there is something in the middle, it will be a middle support. It becomes an internal hinge, and an internal hinge becomes a middle support. So this is how we get the conjugate beam. We get the loading on the conjugate beam and the boundary conditions in a conjugate beam, and we solve the bending moment and shear force in the conjugate beam, and they are corresponding to the displacement and slope in the real beam. That is what we want to find out. In a truss, we want to find out the nodal displacements, and in a beam, at every point, we want to find out the vertical displacement and the rotation or the slope. Then the last part of the phase one was week six, where we look at influence line diagrams. They are basically, yeah. See, there are two kinds of major types of loads. I mean, there are earthquake and wind, other kind of loads, but two kinds of loads that we are always expected to find on a structure. Dead loads, for example, self weight of the structure, flooring, etc. Stationary and constant loads. They basically do not change over the lifetime of a structure. Once you make a building, its self weight is constant. The flooring, the marble, or the tiles, whatever you have put, they are constant. So the variation of bending moment, shear force, deflection along the sections are also constant. You just take, there is a stationary loading pattern. So the variation of bending moment, shear force, whatever you draw is fixed. It is fixed for its lifetime. But live load is another kind of load that is always present on a structure. It is, for example, furniture. The weight of people in a building, the wheel on a bridge, cars are passing by, trucks are passing by, people are walking. The load is continuously changing. So this is the position and magnitude vary with time. So far, what we have done is we have taken a beam or a truss or anything. We have taken a fixed loading pattern and we have analyzed it. But what when the loading changes? We need to study that as well, because in real life, in the real world, when we want to design a beam, we cannot say that this is the load that is always going to be. I mean, this fixed pattern is always going to be formed. We have to consider the variations that can be possible due to the live load, and that is where the influence line diagram comes into the picture. It is a diagram that represents the variation of stress functions such as bending moment, shear force, reaction force, slope or deflection at a fixed section when a unit concentrated load moves from one end to the other end. A unit concentrated load moves, and we are looking at only one section at particular point of time. Here the variation of x is the movement of the load, not the section. And so since we are looking at linear structures, we can say that suppose there are five loads on a structure. If we individually study the response due to each load, and then we add the five, just algebraically add, like with sign plus minus, then we will end up getting the total response. This is what it says. Once we have the ILD of a particular stress function at a particular section, we do utilize principle of linear superposition to calculate total effect due to a combination of loads. So suppose we have the influence line diagram for unit wheel load moving across a bridge. Then we know that suppose a 10 kilonewton is moving, then we can simply multiply the influence line diagram by 10. That is what is called by linear superposition. We can multiply it by a number, or we can simply add two or three load cases, and we can find out the net response in that section. And from that, there are some rules and some guidelines about how to find the maximum stress that can be found at a found that we can expect to find in a particular section, and so on. Then we move to phase two, which is the indeterminate phase. We start with a review of degree of structure indeterminacy. I mean, we looked at it in the beginning as well, but how to calculate the values, exact structure and exact degree of structure indeterminacy for various structures. Then introduction to force and displacement methods. They are the two kinds of the two kinds of approaches that we adopt to solve indeterminate structures. And Maxwell's Betty's reciprocal theorem and method of consistent deformation, that is the force method. So structure in indeterminacy, as we state that structures that cannot be analyzed using statics or equations of equilibrium are called indeterminate structures. They require other material properties to be solved. Basically, when a structure is indeterminate, it means there are more number of reactions than the number of available equations of equilibrium. Then how will you solve it? You cannot just you have only three equations. You have four or more unknowns. Then you cannot solve it by just algebraic equations. So far we have done. So we need some additional properties, like other material properties, to be solved, and that is what phase two deals with. The kinds of additional additional equations that suppose the structure is 3 degree indeterminate. It has three extra reactions than the number of equations. So we need three extra equations to solve the entire system, and this we have already looked at. And this is I mean week 7, 8, and 9 basically deals with the there is a method of consistent deformation that is applied to beams, trusses, and frames, and that is a force method approach, and that is one of the approaches used to solve indeterminate structures. For example, force compatibility or flexibility method is that approach. Redundant forces are chosen as unknowns, and additional equations are obtained by considering the geometric conditions imposed on the deformation of the structure. Compatibility conditions. We already talked about that. Compatibility conditions means that at any point there can be only one displacement of a structure, only one rotation of a structure. I mean, there can be no discontinuity in the structure. That these compatibility conditions are our additional forces basically to solve an indeterminate structure. There are several methods: method of consistent deformation, the virtual work or unit load method, strain energy method, method of minimum potential energy, and the flexibility matrix method. Of these, the only the first method is mostly important. The method of consistent deformation applied to beams, trusses, or frames, and basically we take the number of redundant forces, that is a if the structure is x degree is n degree indeterminate, then we will have n redundant forces, and we will use each. We have to get we will also have corresponding n compatibility conditions, that if we impose on that, we will get the n extra equations to solve the redundant forces first, and then we if we have solved the redundant forces, we will get a determinate structure, because once, as I said, once the reactions have been solved, the structure does not care whether it is a reaction or a force applied to it, so we can just treat it as as additional loading, and we can solve the determinate structure, and then we can find the other responses: the bending moment, shear force, the slope, the deflection, and so on. And the displacement, equilibrium, or stiffness method is different. Here the displacements of joints are taken as unknowns, and equilibrium equations are expressed in terms of these displacement and internal loads. This we have still not looked at. There are 3 weeks still left in the course, week 10, 11, and 12, that will look at these displacement methods. These equations are solved to give the actual joint displacements from which redundant forces can be calculated. And there are three major methods: moment distribution, slope reflection, and stiffness matrix. These three are what we will cover in the next 3 weeks, and they are all very important, unlike this one where mostly the method of consistent deformation is what we use. And virtual work and unit load method is basically worked into the method of consistent deformation. Virtual work is a tool that we have been using in many places without actually taking the name, but it is used in the method of consistent deformation. These are the difference between the two methods. In force methods, unknowns are taken as internal member forces or reactions. In displacement method, unknowns are taken as the joint displacements. In force method, to find the unknowns, compatibility conditions are written, and the number of equations required is the degree of static indeterminacy. That is the number of extra or redundant reaction forces we have. And to find unknowns in displacement method, the joint equilibrium conditions are written, as we will look at in the next few weeks, and the number of equations needed is the degree of kinematic indeterminacy. This method is suitable. Of course, now kinematic indeterminacy is different from static indeterminacy, and since the number of equations is equal to the degree of static or kinematic indeterminacy, we will choose the method depending on which degree is lesser, because that is the number of extra equations we have to solve. So, if the degree of static indeterminacy is less, we will choose the force method, and if the degree of kinematic indeterminacy is less, we will choose the this displacement method. Here we summarize the steps of method of consistent deformation are summarized. First, we find the degree of indeterminacy. That is what we have to do whenever we are given a structure. We have to find the degree of indeterminacy. We choose the statically determinate and stable primary structure. Then we identify the redundance and compute displacement of primary structure subjected to external loading, and redundance separately at those points where conditions of compatibility exist. If we solve the redundance using conditions of compatibility, then it becomes a determinate structure, and we can plot the BMD and SFD by superimposing effects of redundance and given loading on the primary structure. Then, on this, we have solved several problems. It can be applied to trusses, beams, and frames. And now we just take a brief overview of the remaining three displacement methods: slope deflection method, moment distribution method, and stiffness matrix method. This will be gone through into details in the next 3 weeks. So this is just a brief overview. In slope deflection method, we draw the separate parts of a beam in between supports. We compute the fixed end moments. Like we assume that there were two fixed beam is basically a beam that a cantilever beam with a fixed support on both ends. It's not a cantilever beam; it's a beam with fixed supports on both ends. There are methods to compute the fixed end moments. Then we write the moment equations for each beam. This is the format. Then we write the compatibility condition or boundary conditions, and the joints are combined to get zero moments and end conditions. I mean, moment equal to zero or slope equal to zero. That is basically why in the previous approach we were taking the redundancy as unknowns. Here we take the joint displacements or rotations as unknowns, and we conserve that. Then we write the equations in a matrix form and solve for the components. That is another thing. A bit of linear algebra is required, which you have probably covered in your first year of BTech. Linear algebra is, I mean, if you are given a set of equations, if you are given a set of four equations in four variables, and you have a 4 by 4 matrix to be solved, I mean, to be inverted. Of course, it is not easy to do by hand, and if you are expected to do by hand calculation, you will get maximum three equations, but they are written in matrix form to make the solution easier. Then we solve the moment equations, and then we solve the reactions for the beam or frame by using the forces and the moments to find individual components. If this is not clear now, it is fine. Next week we are going to look at the slope deflection method in details. The summary of a moment distribution method is they first assume that each joint is fixed for rotation. There can be no rotation. It is completely moment fixed moment wise. Then by locking and unlocking each joint in succession, the internal moment that the joints are slowly distributed and balanced until each joint reaches a final equilibrium condition. This method is actually carried out in the form of a table. It is a iterative kind of thing, a recursion kind of thing, where the moments are balanced. Every time we balance a moment, something else will get unbalanced. Then we keep on crossing the moments, and at one point we will reach a balanced final an equilibrium condition, which is mandatory, right? Whenever we are solving a structure, what we want is at the end it has to reach an equilibrium where there is no movement, where there is no I mean, they can see deflection and rotation is also a kind of movement, but that is allowed. But equilibrium means there is no global movement. So that is the ultimate condition, right? Ultimate state we have to reach. And this is the stiffness matrix method. In this method, basically, the displacement and joints are simply taken as unknowns, and the equations are expressed in terms of these unknowns. That is, and suppose you have a truss, the number of at each node there are 2 degrees of freedom. Each node can move in the x direction in the y direction. There can be a amount of displacement. So we have suppose a simple three-member truss. Then it will have six unknown reaction, six unknown displacement: 1, 2, 3, 4, 5, 6, one at each joint. Then there will be certain boundary conditions. That suppose there is a hinge support at one end, then there can be no displacement. And suppose there is a roller support on another end, so there can be no vertical displacement at that point. But basically what we do is we take the displacement at each joint as unknowns, and we have to find out a stiffness matrix, a global stiffness matrix. Stiffness, what does stiffness mean? What have we learned in our childhood? That the spring stiffness is the amount of force required to cause unit deflection displacement in the spring. That is the most basic and correct definition of stiffness. So for every truss element, beam element, there is a stiffness we can find out, that we will learn, and we can assemble it into a global stiffness matrix. If there are n degrees of freedom, there will be an n by n global stiffness matrix, and there will be n degrees of freedom that we have to solve, and this is equal to the force matrix. And at each joint we know the force, because in structure analysis, what is given? The structure is given, the loading is given, the boundary condition is given, and we have to find out the displacement and the forces in the members. So the force matrix is given, the deflection displacement force vector is given. We can assemble the force vector. The deflection vector is what we want to find out, and the stiffness matrix we have to find out. We have to find out. I mean, we can find out not by solving, but we know the methods. So f k delta equal to f k matrix into delta vector equal to f vector. This is the matrix equation we have to solve. We solve it by d equal to k inverse f. Yes, basically the assembling of the stiffness matrix is the most important part of this. And once we solve the d, once we have the d vector, we have the displacement at each joint. So once we have that, we can find out the individual member forces and all the entire response of a structure. So I think that is all for the overview of this course. And the last three methods we are going to look at details in the next few, in the next weeks, and that will bring us to the end of the course. The most important topics are still, I would say, the bending moment and shear force diagram is one very basic topic. Influence line diagram is important, and principle of virtual work is very important. And some applications like Maxwell-Betty's reciprocal theorem, it can be especially in competitive exams, entrance exams like GATE. Those certain tools are very important. I mean, because there is a race against time, and they help you to solve the questions easily, quickly. And analysis of indeterminate structures are not that important for the competitive exams because they are very elaborate. They take a lot of calculation. You need to solve a lot of equations extra and all that. But they're important for normal written exams. So uh, I think that is all for this course.